Bomber-shaped aircraft flying over wartime England. Spring 1943. In the spring of 1943, a German bomber appeared over England, then vanished from radar screens while controllers watched in confusion. The aircraft was still there, still flying, but to the electronic eyes scanning the sky, it had simply ceased to exist. How do you build a machine that disappears? World War II British radar operators confused by disappearing target. For nearly a century, engineers and military planners have chased the same impossible dream: an aircraft that cannot be seen. This isn't science fiction or fantasy. It's the story of stealth technology, a revolution that changed modern warfare and redrew the boundaries of what's possible in aerospace engineering. Engineer examining blueprints, pondering invisibility. The quest began in the Second World War and accelerated through the Cold War, reaching its peak in the Nevada desert where a plane shaped like an alien craft first took to the skies. Today, invisible aircraft patrol conflict zones from Eastern Europe to the Pacific, and the technology that makes them disappear is finally coming into focus. Engineers walking through hangar with aircraft mock-ups. The story begins not with invisibility, but with its opposite. In 1940, Britain's radar network could spot German bombers from miles away, giving precious minutes of warning before attacks. The new technology was winning the Battle of Britain, and Germany needed a counter. Faceless pilots standing beside futuristic stealth jet silhouette. A scientist named Hans Hallmann had been studying how radio waves bounced off metal surfaces. He noticed something strange. When he coated metal panels with special materials that absorbed radio energy, the reflections weakened dramatically. By 1943, German engineers were painting experimental bombers with mixtures containing carbon and rubber, primitive radar-absorbing materials that made aircraft harder to detect. Coastal radar tower crew scanning night sky. 1940 Britain. The Americans discovered these coated German planes after the war ended in 1945. Engineers shipped samples back to Wright Field in Ohio and started their own experiments. But the early materials were heavy, difficult to maintain, and only marginally effective. The technology went quiet for nearly 2 decades. Hans Hallmann inspecting coated metal panels in German lab. In 1962, the Soviet Union began developing a new generation of radar systems with longer range and higher sensitivity. American spy planes that had flown with impunity over Soviet territory were suddenly vulnerable. The CIA's U-2 aircraft, once untouchable at 70,000 feet, had already been shot down over Russia in 1960. The message was clear: altitude alone couldn't provide invisibility anymore. German engineers applying radar-absorbing paint in 1943. Lockheed Aircraft's Skunk Works division, famous for building the U-2, started exploring radical solutions. Their chief engineer, Kelly Johnson, believed the answer wasn't just coating but shape. An aircraft's radar signature, the strength of the echo it sends back, depends heavily on its geometry. Flat surfaces reflect radar like mirrors. Curves scatter it in multiple directions. The trick was designing a plane that reflected radar energy anywhere except back toward the receiver. Split-screen lab with coated versus uncoated panels under radar. In 1975, a mathematician named Pyotr Ufimtsev published an obscure paper in the Soviet Union describing how electromagnetic waves scatter off geometric surfaces. The paper had been ignored in Russia but caught the attention of an engineer at Lockheed named Dennis Overholzer. He realized Ufimtsev's equations could predict exactly how radar would behave around any shape. Overholzer's team used Ufimtsev's mathematics to design an aircraft composed entirely of flat panels angled to deflect radar in controlled directions. The result looked nothing like a traditional airplane. It resembled a geometric sculpture, all sharp angles and faceted surfaces, like something folded from black origami paper. Lockheed called it the hopeless diamond because its aerodynamics looked terrible. But when they built a small-scale model and tested it on a radar range in 1976, the results shocked everyone involved. The model's radar cross-section, the effective size it presented to radar, was 1,000 times smaller than a conventional aircraft of similar dimensions. On radar screens, a fighter jet appeared as big as a barn door. The hopeless diamond registered as something the size of a marble. The Pentagon immediately classified the project and gave it unlimited funding. In 1977, Lockheed won a contract to build 2 flying prototypes of what would become the F-117 Nighthawk. The work happened in the Nevada desert at a remote facility so secret it didn't appear on maps. Workers were bussed in before dawn and bussed out after dark. Family members didn't know where they worked. Building a stealth aircraft required solving problems engineers had never encountered. The faceted shape fought every principle of aerodynamics, creating turbulent airflow and unpredictable handling. Lockheed's test pilots said flying early prototypes felt like balancing on a basketball. The aircraft required a sophisticated fly-by-wire computer system to make constant tiny adjustments, keeping it stable through continuous electronic intervention. The coding was equally challenging. Lockheed developed a material called RAM, radar-absorbent material, that had to be applied by hand to every surface. The coating was fragile, expensive, and needed constant maintenance. After every flight, technicians inspected the entire aircraft for damaged panels and carefully repaired any imperfections. A scratch could create a radar signature. Even the smallest details mattered. Traditional aircraft have antennas, sensors, and weapons mounted externally. Every protrusion creates a radar reflection. On the F-117, everything had to be hidden inside. Weapons sat in internal bays that opened only during the seconds needed to release bombs. The edges of every door and panel were serrated like a saw blade to prevent radar reflections along straight seams. On June 18, 1981, the first F-117 prototype lifted off from Groom Lake, Nevada. The test pilot, Harold Farley, reported the handling was difficult but manageable. Over the next 7 years, Lockheed built 59 production aircraft in complete secrecy. The planes flew only at night. If one appeared at a maintenance facility during daylight, crews draped it entirely with tarps. The public first learned about stealth aircraft in November 1988 when the Pentagon released a single photograph of the F-117. The angular black shape looked so strange that many observers thought it was a hoax or prototype that would never see service. They were wrong. In January 1991, F-117s flew combat missions over Baghdad during Operation Desert Storm. Iraqi radar operators saw nothing. Anti-aircraft systems didn't lock on. The aircraft struck targets in the most heavily defended city in the world without a single loss. The footage of precision strikes broadcast on CNN didn't show the planes that delivered them because they flew invisible in the night sky. The success transformed military aviation. By the mid-1990s, Northrop Grumman was building the B-2 Spirit, a flying wing bomber with smooth curves instead of facets. The B-2 used more advanced mathematics and computing power to create curved surfaces that were both aerodynamic and stealthy. Each aircraft cost over $2 billion, the most expensive warplane ever built. The next generation, the F-22 Raptor and F-35 Lightning II, integrated stealth from the beginning rather than adding it to conventional designs. These aircraft had internal weapons bays, serpentine engine inlets to hide turbine blades from radar, and coatings built into composite materials rather than applied afterward. They could maneuver like traditional fighters while maintaining low radar signatures. The evidence for stealth technology's effectiveness comes from multiple independent sources. Declassified Pentagon documents detail radar cross-section measurements showing F-117 signatures between 0.003 and 0.01 square meters, compared to 10 to 15 square meters for conventional fighters of similar size. Combat records from 3 separate conflicts, Desert Storm in 1991, Allied Force in 1999, and Iraqi Freedom in 2003, show F-117 aircraft flew 1,669 combat sorties with 0 losses to enemy fire despite operating over defended targets. The single F-117 lost in combat occurred in Serbia in 1999, when the aircraft flew a predictable route and a radar operator achieved a lucky detection during the brief moment when weapons bay doors were open. Independent verification comes from civilian radar tracking. Aviation enthusiasts with sophisticated receivers have documented F-117 and F-22 flights and confirmed these aircraft are significantly harder to detect than conventional types at similar ranges. However, stealth doesn't mean invisibility. Under certain conditions, with the right radar wavelengths and positions, stealth aircraft can be detected. Russian and Chinese military publications acknowledge the challenge stealth technology poses to traditional air defense systems. Russian defense analysts have published papers discussing the need for longer wavelength radars and networked sensor systems to counter stealth aircraft. This represents indirect confirmation that the technology works as advertised. Not everyone agrees stealth technology lives up to its reputation. Some defense analysts argue the enormous costs, hundreds of millions per aircraft, aren't justified by the capability gained. Critics point out that stealth aircraft require extensive support infrastructure and are vulnerable if detected even briefly. Others question whether stealth remains effective against modern radar systems. Longer wavelength radars in the VHF and UHF bands can detect stealth aircraft at certain ranges, though not with enough precision to guide weapons. Some engineers believe advances in computing power and signal processing will eventually erode stealth's advantage, making the technology obsolete. There are also debates about specific claims. The exact radar cross-sections of operational stealth aircraft remain classified, so public figures come from estimates, leaks, and occasional declassified snippets rather than complete data. Some specifications cited by manufacturers may represent best-case scenarios rather than typical operational signatures. The historical record has gaps as well. Much of the early development work remains classified decades later. Key design decisions, alternative approaches that were rejected, and close calls during development aren't fully documented in public sources. We see the successful result but not the complete story of how engineers got there. The impact of stealth technology extends far beyond engineering achievement. For air defense operators in conflict zones, stealth aircraft represent a threat that appears without warning. Serbian air defense crews during the 1999 Kosovo conflict described the psychological pressure of knowing they were being attacked by aircraft they couldn't track. Several radar operators suffered stress-related health issues during the campaign. For pilots, stealth technology changed the nature of combat missions. F-117 pilots flew alone at night into heavily defended territory without fighter escorts or jamming support. They relied entirely on their aircraft's low signature to survive. Several pilots have spoken about the intense psychological pressure of these missions, flying through radar coverage they hoped couldn't see them. The technology has broader implications for civilian populations in conflict zones as well. Stealth aircraft enabled more precise strikes with reduced risk to pilots, which military planners argue reduces overall civilian casualties by allowing attacks on military targets in urban areas. However, the same capability makes intervention decisions easier for political leaders, potentially lowering the threshold for military action. The ethical implications remain debated in international relations and military ethics circles. Understanding stealth requires grasping a fundamental principle of physics. Electromagnetic waves behave predictably when they encounter surfaces. When radar waves hit an aircraft, some energy absorbs, some passes through, and some reflects. The reflected energy is what radar receivers detect. Stealth technology minimizes that reflection through two methods: shaping that directs reflections away from receivers, and materials that absorb radar energy instead of reflecting it. Think of it like this: a flat mirror reflects your image directly back to you. A disco ball's facets reflect light in scattered directions, never sending a complete image back. A black felt surface absorbs light instead of reflecting it. Stealth aircraft combine the disco ball principle for shape and the black felt principle for materials. They don't make the aircraft disappear. They make the radar echo too weak to detect. The broader significance goes beyond military technology. The mathematical tools developed for stealth design have applications in telecommunications, medical imaging, and even architecture. The ability to control how electromagnetic waves interact with surfaces informs everything from cell phone antenna design to MRI machines. Strategically, stealth technology represents a classic innovation arms race. One side develops a capability, the other develops a counter, then the first side adapts again. China and Russia are now fielding their own stealth aircraft designs. Meanwhile, the United States and its allies are developing next-generation radar systems and exploring new detection methods using artificial intelligence to recognize subtle patterns in electronic noise. The competition continues evolving. We've traced stealth technology from primitive coatings in World War II through the mathematical breakthrough that enabled the F-117's faceted design, to today's smooth-curved stealth fighters operating worldwide. The core insight remains unchanged. Control an aircraft's shape and surface properties precisely enough, and you can make it nearly invisible to radar. What we don't fully know is where the technology's limits lie or how long stealth will maintain its advantage as sensors improve. The physics is understood, but the engineering details of the most advanced systems remain classified. We're watching an ongoing technical competition with high stakes. That competition is about to enter a new phase, one involving not just invisible aircraft but invisible networks. In the near term, the most likely development is continued refinement of existing stealth designs. The F-35 will remain in production through the 2030s, with software updates and coding improvements extending its capability. This represents incremental evolution rather than revolution. The United States Air Force is developing a next-generation fighter under a program called Next Generation Air Dominance. Details are scarce, but the program aims for aircraft that are even harder to detect and can operate as network nodes, sharing sensor data across multiple platforms. These aircraft will likely fly by 2030. A more speculative possibility involves active stealth systems that don't just reduce radar signatures, but actively cancel them using sophisticated electronic interference, similar to noise-canceling headphones for radar. Several research programs are exploring this concept, but it remains in early stages. Whether it's practical for operational aircraft is uncertain. The counter-stealth side is advancing as well. Quantum radar systems, which use entangled photons instead of conventional radio waves, could theoretically detect stealth aircraft by methods that current designs can't defeat. However, whether this technology can work at practical ranges and scale to operational systems is unproven. What's almost certain is that the stealth versus detection competition will continue. Neither side will achieve permanent advantage. Each breakthrough enables a counter which drives the next innovation. The only question is which specific technologies will define the next phase. The quest to build invisible aircraft succeeded not through a single breakthrough but through decades of patient engineering, solving thousands of small problems to achieve one extraordinary result. The technology changed warfare, but it didn't end the fundamental competition between those who want to see and those who want to hide. If you found this story compelling, watch our investigation into the radar system that shouldn't have worked to see the other side of this technological arms race and learn about the detection methods that challenge even the stealthiest aircraft.